Okay, so I want to talk about nuclear reactors. Okay, so a couple of important points first to explain what's going on. We have the fuel, which is uranium that has been mined. But uranium that has been mined, as we mentioned already, contains uranium-235 and uranium-238. Most of it, 99.3% of it, is uranium-238, and only 0.7% of it is uranium-235. Uranium-238 will not undergo fission. Uranium-235 will undergo fission. It will undergo fission whether it has fast or slow moving neutrons. Okay, but uranium-238 absorbs fast moving neutrons. So if the majority of a sample is uranium-238, then even if a uranium-235 atom undergoes fission, because when the uranium-235 undergoes fission, it produces fast-moving neutrons, then those fast-moving neutrons are less likely to get to a 235, another 235 nucleus, before they get to a 238, because the majority of the sample is uranium-238. So uranium-238 will absorb the fast-moving neutrons that have been emitted from a fission of a 235 atom, and those neutrons will not get to further create fission with a 235 uranium atom isotope. So uranium-238 will not absorb slow-moving neutrons. Slow and fast-moving neutrons will cause fission. So what we would like to do, if we want to create a chain reaction that's going to produce lots of energy, we would like to make sure that the neutrons that are released from the uranium-235 are slowed down. Otherwise, they'll be absorbed by the 238 in the sample and they'll never get to further produce fission. So we want slow-moving neutrons. We also need a higher percentage of uranium-235 in this sample. Okay, so what we get naturally is not enough, and we need to enrich the uranium that we mine naturally so that it has a higher percentage of uranium-235. Now, I've heard the percentage 4%, but I'm not sure. So take that with a pinch of salt. I should really look that up, but you guys can look it up. So we will enrich the sample, the uranium, the fuel. We'll enrich it so that it has 4% 235 isotopes, and obviously in that situation then it would be 96% of uranium-238. Okay, so the fuel is a rod like this, and it is enriched natural uranium. The fuel then, we know, again as mentioned, if we leave things as they are, the uranium-235 will undergo fission, it will produce fast-moving neutrons, they will be absorbed by the 238, which is the majority of the fuel, and they will not get on to cause further fission. So we need to slow them down. This is function of the moderator. This is the moderator here. Okay, so the moderator slows down the neutrons that are produced during fission. Slowing them down means when a neutron is produced, it's slowed down so that when it hits the fuel, when it enters the fuel again, it will now have a higher chance of causing fission because it will not be absorbed by uranium-238, which only absorbs fast-moving neutrons, and therefore it has a likelihood of getting to a uranium-235, which will undergo fission whether it's a slow or a fast-moving neutron. Okay, that's the moderator. The moderator is made from what's known as heavy water or deuterium. Okay, and basically it slows the neutrons because it gets in the way and causes them to collide and lose some of their energy, and they move slower. Okay, then we have the possibility of things getting out of control. Okay, we might have too much fission occurring, and the reactant can just give off too much energy and basically create havoc. So we need to be able to control the level of the chain reaction that's taking place, or the rate of the reactions. So the control rods are made of a material that actually absorb neutrons. So they make less neutrons available for fission. So the control rods can be slid down over the fuel rods, and they absorb neutrons. So the more of the control rod that's down over the fuel rod, the less available neutrons that can go out from the fuel and cause further fission, be slowed down and cause further fission. Okay, any neutrons created up here will be absorbed by the control rod. So the control rods go down and up depending on how you need to control the reaction. If the reaction is too slow, you pull them up. If it's too fast, you start moving them down. You then have a coolant which is circulating. Okay, the coolant is circulating in here, and that gets hot because the daughter nuclei fragments from the fission of 235 are moving with a very high kinetic energy, and they will collide with the coolant, the atoms of the coolant, and make the atoms of the coolant extremely hot. The coolant is pumped constantly around, so it's basically, as it comes out here, it's very, very hot. It loses its heat out here to the liquid that is in here, okay, which is water. And that water is being pumped in separately in here, and it comes out as steam, okay, because it's being heated by the coolant that's circulating around here. So by the time the coolant gets down here, this would be a lot more of a distance to travel than what's drawn here. The coolant comes in and it's colder again. It then gets heated up again by the daughter nuclei and the fragments coming off from the reaction. And basically, as it comes out here again, it's hot, and it releases its heat to the water in here. And effectively, the water coming in here is heated by the coolant and then turns into steam, and the steam is used to turn turbines, which either turns a coil in a magnetic field or turns a magnetic field around a coil, either way producing electricity in the coil. And I'm going to stop now in case I go too far.